Okay, so in last video, we studied this equation, and I promised that I will use this equation, and then apply it to the Newton's law to show you that the Newton's law actually behaves different in rotating frame. To know that, let's look at the translational dynamics of vehicle first. This is the translational dynamics of the aircraft, where this is the force, the external force applied on the vehicle in the body frame, on x-axis, y-axis, and z-axis. Then this is the velocity vector with respect to the ground in body frame, and then this is the rotating angular rotation speed. It can be decomposed into those three directions as well. And again, this is like the relative rotation of the body frame against the inertia frame expressed in body frame. And this equation might look very strange to a lot of you, but after this video it will become clear that it is all derived from the Newton's second law in the inertia frame. So we will help you understand this. If we think about the Newton's second law, right, the force, if we have a force vector that is in the body frame, it is not in the body frame. Let's talk about that in the inertia frame first. So that is the Newton's law that most people are familiar with, which is equals to the mass times the acceleration, and the acceleration itself is equals to the derivative, in this case all the quantities inside of the inertia frame, so derivative with respect to the inertia frame, and derivative using the velocity vector. And for simplicity, we usually make this inertia frame essentially with respect to inertia frame the G, the ground. So because we assume the ground itself is the inertia, and we ignore the effect of the self-rotation of the Earth, which is relatively slow against the aircraft. So this governing equation, I think if you studied the high school physics, you will understand it. It's the force is equals to mass times the acceleration. Going from here, we will derive those. So what if we are interested in the body frame, like the force expressed in body frame, that is equals to the mass, and then you take the derivative, this in this case take derivative against the inertia frame, but the ground speed will be in the body frame, because there is always a rule that if you express this term in body frame, the other term needs to be in the body frame as well. However, this means that the observer stands in the inertia frame. The vector itself, the force vector, as well as the Vg, the velocity vector, is expressed in the body frame. However, the human or the observer is in the inertia frame, is on the ground. So in this case, we will apply the equation that we got from last time. If we take this conclusion here and apply it on the velocity vector. That will be equals to the mass multiplied by, in this case, we're not talking about the general vector p, but we're talking about the vector vg b, the velocity vector. And then that will be equals to, you take derivative, but the observer now is inside the body frame, where the velocity vector is also in the body frame, projection in the body frame. So there is no relative motion of velocity vector and the time. So in this case, you later on, if we understand, if we expand it, there is no effect of motion. However, the effect of motion is separated out in this term. The effect of the frame change, taking into the fact that the frame body frame is rotating against the inertia frame, and then that is equals to the omega vector b dash I, expressed in the body frame, cross product with the in this case the vg b itself, that vector. So then we got the Newton's second law in the body frame, when the observer, is in the inertia frame. So this is the rotating effect, frame rotating effect. This is, the normal derivative portion. So let's move on. And you see, these two equations are already very similar. It's just, because we are interested in the dynamics, meaning that we're interested in the change of the velocity. So it's just a matter of making this one to the left. So f dash b 1 over mass, right? And then minus omega bi dash b, and cross product the vgb, right? So this portion will be equals to the time derivative of ground speed expressed in body frame against with respect to body frame. So this equation we have already sort of proved is the same as this. Now let's talk about how to go from the vector format to the scalar format. And that's sort of easy by just using those definitions, right? In terms of visualization, it's quite straightforward. If you apply a force, right? If this is your inertia frame, north, east, and down, right? It's down to the ground. And your rotating frame, if it's rotating against a certain axis like that, right? It's rotating using the so-called right-hand rule. So your positive rotation is defined like right-hand rule. And then we talked about this is the whole vector, meaning you have a frame that is rotating against this axis. We introduced this in last video, so it's just like a sort of a review, right? So this is rotation, rotation, as well as rotation. And when we have this vector, when we say it is B here, we mean that we project the rotation vector onto this rotation. Sorry, this rotation vector. We can project it onto the body frame, where we project this onto body frame, onto body frame, onto body frame. So you just apply projection, and each of them can be again modeled by right-hand rule as a rotation quantity. sum point to the direction. And this rotation, how fast in that direction, IB, this unit vector direction, is modeled by P, Q, and R, right? In those axes. So east axis is G-B is the rotating axis, and I should use the color, the red color. Right? So similarly, you can decompose the force vector and as well as the ground velocity vector of your aircraft onto those body axes, because we know that the body axis just moves together with the aircraft itself. And if you are not familiar with body frame, you go back to review body frame video. And then with that, we can expand a little bit from this vector format. The VG is like UVW. That's why we can express this part as like a U. This is like the time derivative. So U, V, and W. And these are all in the body frame. And for example, this UI, this VG is like the U, V, and W. This U dot is actually DU, DT in the body frame itself, because both VG as well as the time is inside the body frame. There's no rotating effect. It's just take the derivative itself. And this is equals to the tricky part is actually the negative this cross product part. Let's worry about that a little bit later by just derive this part first, which this is just fx, fy, and fz, again in the unit direction of the body frame. And then it comes to because we are trying to derive the state equation, the states are the u, v, and w, and then all we left is fill out this matrix. And this is like derived from this term, negative omega, the rotation of the body frame against inertia frame expressed in body frame or projected on the body frame, and then cross product with the ground velocity vector and expressed or projected on the body frame. This is equals to actually the velocity, right? The velocity is also defined as in this case PQR. So it's really the let's say the negative, and then we have the PQR for the IB height plus the QGB height plus the in this case it's the R KB height cross product with the vector U IB height plus the V JB height plus the W KB height. So they are all in body frame. And then we apply something called cross product. I had a video review cross product as well, but essentially mathematically we have to compute the cross product in 3 dimension, which essentially there's a quick way you can do that. It's equals to essentially write it into a sort of matrix format like that, and then you have PQ and R, then UVW, and then what we usually do is apply across like that. So you compute the determinant of the 2x2 matrix, which will be equals to the QW minus RV times the IB height, and then you have, cross G out. You have the P and W RU, right? So P W minus RU inside the GB, and then you will have the last direction, cross that out, and then you have PV minus QU. So PV minus QU times KB height. And this is, there's different ways to achieve this result, but this is the easiest way you can do. Just remember this trick. And then we have negative sign there, which cannot be forgot. So that forms your equation for forming that matrix, right? Because all these vectors, scalar vectors, are essentially having directions. So this is like IB, GB, and KB, right? And then UVW, this first term without U, so this is 0, V times R and W times the Q, and then you have the R, negative R times U. Actually, I made a mistake. Sorry, this is negative. Let me make this RV minus QW, right? Then IB height, plus the RU minus PW times the JB height, plus the QU minus PV times KB height. And then we know here is a little bit different. It is essentially still 0, and then RV negative QW, and then the RU and 0, and then negative P, right? And then QU minus PV, which is the Q here and P here and 0 here. So and I made a mistake at the beginning right here, so I need to correct that. It is actually R negative Q negative P, and then RQP at here. Right? Alright, so that's how we proved the translational dynamics of the aircraft by leveraging the conclusion that we got from the lecture differentiation of a vector. Physically speaking, this is essentially model the how the external force on your plane in the body frame, how your external force can affect the dynamics of your ground speed, right? So that's the physical meaning of all this. Thanks.